Hello everyone. I'm very happy to share my recent result on Succinct blind quantum computation using random oracle. I'm Jiayu Zhang from Boston University. So what is blind quantum computation? In this problem, a client has a quantum circuit C, and he wants to evaluate it and get C0. But he doesn't have the ability to apply C itself. So it makes use of a remote quantum server. But on the other hand, it doesn't trust the server and wants to keep C secret. So it wants to design a protocol to interact with the server to get the result. This problem is very important in quantum cryptography. First, the problem itself is very important. It's very possible that, in the near future, quantum computers can only be used as a cloud service. So if we want to make use of the power of a remote quantum server, simultaneously want to keep our data secure, such a protocol is needed. What's more, this problem has become the testbed for new techniques that can be later applied to many related problems. For example, quantum computation verification, which is considered to be a very fundamental problem in the theory of quantum computation. In more details, there are three minimum requirements for this problem: coherence, security, and efficiency. Coherence means when the server is honest, the client should get the correct output. For security, we use a common security notion in cryptography, the indistinguishability-based security, which means the malicious server could not distinguish whether the protocol is run on real input C or is run on a zero string. And we also require the efficiency, which means all the honest computation is upper bounded by a fixed polynomial of the circuit size and the security parameter. And these are just minimum requirements, and there are still many different settings. In this paper, we give a new ubiquitous protocol where the client-side quantum computation is succinct and is secure in the quantum random oracle model. Let's give a review of existing works. We will focus on universal protocols using only a single quantum server. Existing works can be classified into two classes. One class is IT-secure protocols. One representative of this protocol is the ubiquitous protocol by Broadband, Feisman, and Carriffy. In this protocol, there are two phases. In the first phase, the client only needs to prepare and send some simple quantum gadgets. And in the second phase, the client can be completely classical. But one problem is, in the first phase, the client-side quantum computation is linear to the size of the circuit. And this seems to be inherent for IT-secure protocols, because as far as we know, this relation holds for all the existing protocols in this class. And another class of protocols is protocols based on trapped assumptions. An early representative is a protocol by Dulac, Schaffner, Spearman. And recently, Hadamard gave a protocol where the client can be completely classical, and the assumption is aligned with error assumption. So let's focus on assumption. There are mainly two kinds of assumptions in cryptography: public key assumption and symmetry key assumption. Let's give an overview. And we will use the message transmission problem as an example. The symmetric encryption, for example, the AES encryption scheme, allows both parties to transmit long messages securely using some initial shared random keys. But if two parties want to transmit some message without assuming the existence of initial random keys, they need to use public encryption. Some examples of public Public encryption includes the ending with error assumption and the RSA scheme, which is broken by Shor's algorithm. So as we can see, existing works on computationally secure ubiquitous schemes are based on public encryption. Thus, we can ask the following question. What if we only have symmetric encryption? And later we will model symmetric encryption schemes as a random oracle. And we also have an extra goal. We want our protocol to be better than the existing IT-secure protocols in terms of the client-side quantum computation. So we can classify different protocols as follows. As we can see, there are different trade-offs between client-side quantum computation and assumptions in this problem. The bottom left corner is a BFK protocol, and the top right corner is a Mahadi protocol. And in the bottom left corner, this paper gives some negative evidences on the implausibility of IT-secure protocols with a classical client. And our protocols reveal the new trade-off in this problem. Here, the quantum random oracle model is used as an ideal model for symmetric primitives. In more details, our protocol is as follows. First, it's quick and efficient, and there are two phases. In the first phase, the client will prepare and send some quantum gadget to the server. And these gadgets can be prepared using only polycappa gates. Poly is a fixed polynomial. Then both parties do classical interactions. And this protocol is secure against a bounded adversary, which makes sub-exponential number of random oracle QRYPTs. So what is the quantum random oracle model? This model is raised in this paper as a generalization of classical random oracle model. In this model, both parties can curate an oracle which encodes a random function. This is the ideal model for hash functions or symmetric encryption. This is the formal setting. We can design protocols in this model and prove the security formally. And in practice, we instantiate a random oracle with head function or block cipher and claim the security heuristically. On the other hand, there do exist some uninstantiable constructions. But in practice, the quantum random oracle model and classical random oracle model has been studied for a very long time and are very successful in practice. So let's go to our construction. In our construction, we want to allow the server to prepare some gadget in the following form. The client will sample two different random strings as the keys. The server will hold the superpositions. And this was used previously in this paper, etc. And the top-down overview of our protocol will be as follows. First, the client will prepare and send some initial quantum gadget to the server. The number of these gadgets is only polycappa, where poly is a fixed polynomial. Each gadget is of the following form, and the keys are different. Then both parties use some classical interactions to expand the number of gadgets securely. And this step is called the remote gadget preparation. Then both parties can use this gadget to perform gadget-static secure computation. In the first step, the remote gadget preparation step is further constructed using the following idea. We first design a protocol that is weakly secure and gadget increasing. Then we use some techniques to amplify the security of this protocol to a fully secure one. The remote gadget preparation step is the most difficult step of this work, and the gadget city computation step is actually also not trivial. So we can give an informal illustration here. Initially, the server has some gadgets, and both parties execute some protocols, during which the number of gadgets get increased, but the security of some keys become weaker. And in some other part of this protocol, the number of gadgets get reduced, but security is improved. Finally, the server will hold many fully secure gadgets again, and the number of gadgets become bigger than initial. And both parties can repeat this protocol and get the gadgets needed. We note that the gadget increasing step and the security application step are actually interlaced in some way. So let's go to the technical details. To construct our weakly secure protocol, we'll use a robust reversible up table and petty Hadamard test to get the first weakly secure protocol, and use a parallel repetition technique to make it gadget increasing. So before we go to the details, let's give an overview of some background knowledge. Cover tables are a very fundamental primitive in classical cryptography. In this construction, two keys are sampled for each wire, which correspond to the input 0 and input 1. Then for each gate, we compute a table, where each row is an encryption of some output keys under the corresponding input keys. Here E is a multi-key encryption scheme with a key verification procedure. Thus, we can imagine this table encodes mapping from the input keys to output keys. So given one input key combinations, the server can try to decrypt each row until the decryption succeeds and get one output key combination. So first we want to generalize it to quantum world, where we introduce the concept of reversible goblet table. In this construction, the gobbling of each gate contains one forward table and one backward table. This construction allows the server to apply the goblet tables on quantum state. Given a quantum state which encodes the superposition of key combinations, the server can first use the forward table to compute the output keys, then use the backward table to erase the input keys. Overall speaking, this construction allows the server to map the input keys to outputs quantumly, which will be useful in our construction later. So let's begin our construction. Our goal is to find a protocol that is weakly secure, gadget increasing. One attempt is to simply use a reversible goblet table and take the input gadget to some output gadgets. But reversible goblet table could not have more output numbers than its input. As was shown here, for example, we gobble Toffoli gate, and it can only take 3 input gadgets to 3 output gadgets, which is not gadget increasing. So we need to do more to increase the number of gadgets. We introduce the following construction called robust reversible goblet tables. In the output part, the client will gobble Toffoli gate and set up additional bitwise computation to protect the keys on the second and third output wire. Recall that keys are not just singletons, but also bit strings. With this construction, our only server can still map 3 gadgets to 3 gadgets, but 2 of the output gadgets are protected under this bitwise computation. With this construction, the client can actually save the cost of preparing one input gadget. Let's see this diagram. The client will prepare one robust reversible goblet table. And for the input part, for 2 of the input wires, the client uses input gadget. And for the second bar, the client will simply provide the description of these two keys to the server, and ask the server to prepare the gadget. And on the output part, the server can use this information to map this input gadget and input keys to this output state. And we can do an intuitive security analysis for that. If the attacker wants to break this construction, one way is to simply measure the input state. And for example, it can get keys x11 and x03. Then the attacker can decrypt the following two rows from the garbage tables. And we can see that because the attacker does not know the hidden permutation, it can't slice out the corresponding keys from these two long strings, which means it can only decrypt two rows in the forward table and two rows in the backward table, and the other rows in the garbage table will still be hidden. But one problem is, in this construction, the output states are still under the bitwise permutation, which is not exactly the formal 3 output gadgets. So we still need to do more to improve the protocol. And this extra step is called the petty Hadamard test. This is the petty variant of the Hadamard testing paper in this paper. We observe that this subprotocol has a property which we call proof of unknown for some key pair. Informally, if the adversary wants to pass this test with a probability, it has to give up part of its ability to predict the keys in this key pair. And if we go back to our construction, this further implies that, informally, the adversary will lose part of its ability to decrypt the garbage table. So with this subprotocol and the robust reverse garbage table, we can actually construct a weakly secure protocol. And after we get the weakly secure protocol, we will amplify the protocol to a fully secure one. The amplification is called the repeat and combine technique. And overall speaking, we give a new ubiquitous protocol for very large circuit, which includes any polynomial size circuit. And this protocol is correct and efficient, and it contains two phases. And the client-side quantum computation in the first phase is succinct, and the second phase will be completely classical. And the protocol is secure against a bounded adversary that makes sub-exponential number of random Merkle qubits. And there are some open questions. Our result naturally gives rise to the following open questions. Could we get more understanding of this table? We still do not understand what is impossible in the blind quantum computation problem. Even if we already have some negative evidence on the classical client anti-secure protocols, these evidences are still very far away from ruling it out. So more understanding of this problem will be very interesting. Thank you.